Hey guys, today's video is about model evaluation. In specific, we'll talk about ROC curve. It's the visualization of the model performance, and it's often used for selecting the best cutoff of a test. Before we get started, I want to first review the concept of confusion matrix. As you may remember, confusion matrix is a tool used to analyze the performance of a binary classifier, and it's a 2x2 matrix with actual class and predicted class on the axis, but there is no guarantee whether the actual class will be on the horizontal or vertical axis. Importantly, the positive data points that are incorrectly classified as negative are called false negative because they are false predictions and they are predicted as negative. I'm sure you can infer the rest on your own, but if you are confused, please check out my previous video, Model Evaluation 1.1. Alright, let's dive into the ROC curve, which is the abbreviation for Receiver Operating Characteristic Curve. Basically, ROC curve is used to choose the optimal cutoff of a test. For example, we have an income dataset and we want to predict the gender of a person based on the income. Then, we have to pick a cutoff, such as people that have annual income more than 100 grand are male. But which is the most appropriate cutoff? This is when ROC curve can help. I know it sounds pretty abstract, so let's discuss why do we need the ROC curve. Suppose we have this medical data with 10 participants. We want to know whether a person is infected by looking at the test number. In specific, test number ranges from 0 to 1, and the infection result is either positive or negative. Positive means that person is infected. To make the data more understandable, I convert it to a scatter plot. The x-axis is the participant, and the y-axis is the test number. Further, the red points are the positive data, people who are infected, and the blue points are the negative data. It's obvious that red points locate at the top of the graph. In other words, people with higher test number tend to be infected. However, how do we decide the threshold or the cutoff? Which criterion should we choose? Before answering this question, let's see what happens if we set the cutoff as 0.6. By setting the cutoff as 0.6, people with test number higher than 0.6 will be classified as positive, otherwise negative. The best case is that the points above the cutoff are all red, and the points below the cutoff are all blue, because that means this cutoff perfectly classifies all the data. In this case, there is one blue point above the cutoff, and there is no red points below the cutoff. So this cutoff is doing pretty well. It almost classifies all the tuples correctly. To be more precise, we can draw a confusion matrix like this. You can see 9 people are correctly classified. Only one person is incorrectly classified. Since we now have the confusion matrix, we can actually calculate a lot of performance measures, such as the accuracy, error rate, recall, and precision. However, how are we supposed to compare the cutoffs? Should we plot a confusion matrix for each cutoff and compare whatever performance measure we choose? That sounds pretty exhausting, but let's repeat the process again anyway. Now we assign the cutoff as 0.8. This time, all the blue points are below the cutoff, which means they are correctly classified. Unfortunately, one red point is below the cutoff, so it's incorrectly classified as negative. Once again, this cutoff is almost perfect, and the confusion matrix is like this. If you think about it, there are infinitely many cutoffs. Instead of 0.1, 0.2, 0.3, we can assign 0.001, 0.002 as cutoffs, and the calculation and comparison would be almost impossible. Nevertheless, we can save the effort by observing the nature of the data. The orange area here, which is roughly from 0.4 to 0.7, doesn't contain any data. No matter you choose 0.45 or 0.5 or 0.65 as the cutoff, the resulting confusion matrix will be the same. Thus, we can save the computing time by only considering the cutoffs that make difference. But don't get too excited. This example only has 10 data points, so we can easily find the insignificant cutoffs. Imagine the database has 10,000 data points. We may still have thousands of meaningful cutoffs, and it's unlikely for us to derive a confusion matrix for each cutoff and compare them. Consequently, we need other measures to help us select a better threshold or cutoff, which is exactly what ROC curve does. To keep the video short, let's stop here for today. In the next video, we'll discuss how to draw a ROC curve and how to interpret it. Thank you for watching my video and see you soon.